So let's continue. So now I have the pleasure to introduce Dr. Matthew Colless. He's a very famous name for people in my area, which reads papers about big redshift surveys of galaxies. The name Colless is always involved in the state of art of these researches, and this kind of data allowed him to do several studies on galaxy evolution and the largest scale of the universe. So now he is going to talk about that kind of science, and as well about the MANIFEST instrument, which he's very heavily involved. Thank you. And he's from the Australian National University.
Hi, can you all hear me? Good. So yes, it's a great pleasure to be here. This is my third visit to Brazil, but my first visit to São Paulo. So it's a great pleasure to be here and to be able to speak at this meeting and to talk about GMT, which is something that I have now been involved with for, oh dear, 12 years already. I got involved when Australia first started looking at extremely large telescopes and trying to decide which of the telescopes we wanted to be involved in, and we decided, for reasons that have not changed over that 12-year period, that GMT was in fact the best of the large telescopes of the next generation for our country to be involved in. And in fact, I have been a PI for one of the GMT first generation instruments now for a decade. As I'll talk about in the third of these lectures, I first came up with the concept for MANIFEST back at a workshop in Australia in 2008. But I'm actually talking about two instruments today, well, not today in this course of lectures, one of which is MANIFEST, which is an instrument that I originally developed, but the second one is GMTIFS, the GMT integral field spectrograph. And that's not an instrument that I'm directly involved in, but it is an instrument that my institution, the Australian National University, is leading. And it was originally developed by my good friend, Peter McGregor, who sadly died a couple of years ago. So I'm going to be talking about sharp images, which is GMTIFS, and wide fields, which is MANIFEST. And I'll be trying to do a number of things. One of the things I want to do is I want to explain why sharp imaging, i.e. adaptive optics, and wide fields, i.e. multi-object spectroscopy and integral field spectroscopy, are important for GMT and for extremely large telescopes generally. The second thing I'd like to do is I'd like to show how the science goals and instrument constraints interact. When one reads about instruments, one gets an idea that there was a brilliantly clear set of science goals that were derived, and then a perfectly well-matched set of instruments constraints were developed, and it was all a very linear and straightforward process. And of course, none of those statements is true. It's an interaction. It evolves in a somewhat Brownian motion way, and I'll show you a little bit of that in the course of these three lectures. The third thing that I'd like to talk about are two types of science outcomes that one hopes one gets from instruments. One of these is what we might call the extrapolated science, based on our current knowledge of the field and the expected capabilities of the instrument. And this is critical for developing the instrument, for thinking about it, for all the things you do to justify your instrument and its funding. And it's almost invariably not what you do with the instrument, and Rebecca has already mentioned this. The second type of science outcome is the discovery space. This is what your instrument can do that nothing could have done before. No instrument heretofore has been able to do this. And with that new ability, we can discover new things. But of course, because you haven't been there before, you don't know what they are. And so that's always the most exciting part, but the hardest part to convince the funding agency to do. I'm going to build this great instrument. What are you going to discover? I don't know. Isn't a great argument. Nonetheless, it's in fact why we really build these things. Astronomy is a discovery science, and all the best results that come out of new instruments are in fact in that second space. So I've got 3 lectures. So this one's going to be an introductory one. I'll talk about sharp images and wide fields, and then I'll use the next 2 lectures to talk about each of the 2 instruments, GMTIFS and the MANIFEST fibre facility. So what I'm going to cover in this lecture, after this introduction, is I'm going to talk about how we get sharp images. So I'm going to do a very brief introduction to adaptive optics. I think Rebecca will probably do a far more detailed and professional one in one of her talks. But I want to give you the background for it so that you've got at least an understanding of not how it all works. I'm not expecting to turn you into adaptive optics scientists, but rather to give you a good feel for why it is good, where its limitations are, and what of the various flavours of adaptive optics might be useful in your science. Then I'll look at wide fields, and I'll look at the development of multi-object spectroscopy and integral field spectroscopy as it applies to ELTs in particular. And then I'll have a quick look at the GMT instrument suite and show how GMTIFS and MANIFEST fit into that. And then I'll do a quick run through the science that can be done with GMTIFS and the science that can be done with MANIFEST before summarising. Thank you. Okay, so let's get on with this. So these are the 3 legs of the GMT science case: the contemporary science goals, what I called the extrapolated science, the discovery space, and a 3rd leg which I haven't mentioned, which is the synergies, the relationship between GMT and JWST and LSST and all the other facilities that will be available in the same space. As Rebecca pointed out before, telescopes are getting larger. The doubling time is about every 35 years, and in fact, I'm happy to see that GMT is a little bit above the curve on this particular plot, because it's got a little way to slide to the right on the time axis, I suspect, but it will still be on that doubling curve quite adequately. And as Rebecca emphasised, one of the main reasons for making bigger telescopes is greater sensitivity, but also, as this is particularly the case for GMTIFS, also greater angular resolution. And as Rebecca pointed out, those 2 things go together and can give you, in the right circumstances, gains of up to a factor of d to the 4th, where d is the diameter of your telescope. But in going that way, one's fighting against the other great difficulty of larger apertures. It's harder and harder to keep a very wide field of view. I'm currently about to launch into a new project on the UK Schmidt telescope, a 1.2 metre telescope optimised for a wide field of view, and it's got a 6-degree field of view. With GMT, all we're going to get at most is a 20 arc-minute field of view, and we've fought very hard to keep that, because that relatively wide field of view of GMT is one of the ways in which it is in fact superior, as I think Rebecca will talk about in much more detail later on, to the other extremely large telescopes. Telescopes themselves don't go through straight-line evolution. GMT is itself the result of a complex process which I've grossly oversimplified here, which started out with the idea back at the time the first 8-metre class telescopes were just coming online. People said, so what's next? And the answer was, 20 to 30-metre telescopes, and the original one of these in the US sphere was the Giant Segmented Mirror Telescope. Then there was an idea called the 2020 telescope, which was a 20-metre telescope to be on the sky by 2020, and that eventually evolved around about 2005, 2006 into the Giant Magellan concept. Oops. And there we go. There we go. So here's the collection of apertures, both historical and current, and you can see where GMT fits into this menagerie. Here's the Giant Magellan Telescope. The dotted circle shows you the equivalent aperture. It's 22.4 metre filled aperture if you count by the collecting area, and it's a 25.4 metre aperture if you count by the largest diameter, which gives you the limiting resolution. So a 25-metre telescope is a nice round number to work with. But of course there are 2 more ELTs being built, the 30-metre telescope and the European Extremely Large Telescope at 39 metres, both of which are larger than GMT. So we need to have ways in which we are superior to those. And as I've mentioned, one of those is the field of view. And the other, of course, is that we hope to be first on sky, and that can make an enormous difference. These are the first generation instruments, the full collection here. We're hearing about GCLEF from Andy St. Georgi. We'll hear about GMT-NIRS from Dan Jaffe. These are the two that I'll be talking about, the MANIFEST Fiber Facility System and the GMTIFS AO-fed IFU spectrograph and imager. And I think Rebecca will pick up the one that doesn't have a PI here, which is the GMAX Visible Wide Field Imager. Between them... Oh, Claudia's going to talk about that. Excellent. Someone is talking about it. I will, in fact, mention a little bit about GCLEF and GMAX because those are the two spectrographs that MANIFEST is coupling to in the first generation set. All right, so let's think about the first of my two topics, which is the sharp images from adaptive optics. So adaptive optics is the key technology. It makes sharper imaging, ranging from a little bit better than natural seeing through to almost diffraction limited. And it's critical for large telescopes if we're going to get the full power out of them. And indeed, for telescopes larger than GMT, you essentially have no choice but to use adaptive optics if you're going to keep your instruments at a scale that can be easily worked with. So I'm going to quickly run through how adaptive optics works and the main types of adaptive optics. So I'll explain these slightly mysterious AO labels, LTAO, MCAO, MOAO, and GLAO, and I'll give you, I hope, a little bit of an idea of when they're appropriate and in what circumstances they might matter. And I should say that I've stolen many of these slides from people who know a lot more about adaptive optics than I do, namely Claire Max and Francois Rigaud. Okay, so basic introduction to adaptive optics. We need adaptive optics to get rid of the blurring in the Earth's atmosphere. It's what makes stars twinkle, it spreads out light, and it makes our images blobs rather than those lovely sharp point source images that we'd like to have. These blobs are a lot larger than the point spread function, which for a perfect telescope in space is limited only by the size of the telescope. So even the largest ground-based telescopes have got no better resolution than a 25 centimetre telescope. And I'll explain why that is in a moment. That means that in building a 25-metre telescope, we are, without adaptive optics, failing to make use of its scale by 2 orders of magnitude. So what happens when nice parallel plane waves from space hit our atmosphere full of turbulence and index of refraction variations, which is what turbulence produces? You end up with a distorted wavefront. The rays are not parallel. They're pointing every which way. And that means that instead of coming to a nice point focus, as they would with our optics, which are designed for parallel rays, they come in at slightly bent angles and so focus in slightly different places. You end up with a blur. Now, this comes from the temperature fluctuations in small patches of air, and that temperature fluctuation changes the index of refraction, and that means the air is acting like a huge pile of tiny little lenses that your telescope is peering through to see your star. And those light rays are then being refracted many times by small amounts. They're doing a random walk through the atmosphere, and so when they reach that, when they reach your primary mirror, they're no longer parallel, and so your telescope, which doesn't know that they're not parallel, doesn't bring them to a point focus. So in fact, what you get when you look at images of a bright star and take very short exposures, speckles. When you take a long exposure image, you get a blurred out Gaussian or Moffat profile like this. But if you take very short snapshots, what you're getting are speckles. And each one of those is the image of your star, close to the diffraction limit, taken through a different coherent patch of air. And if one could only line up all those speckles and add them up on top of each other, then you would in fact get something very close to a diffraction limited image. So here's a movie of speckles. You can see that in each instant in this movie, the image is moving around. There's a whole lot of little bright point sources blurred out into a large blobby image, and that from moment to moment, as you do different integrations, the image is jumping around, the centroid's moving around with time. So the image appears to be dancing around like a drop of water on a hot grill. So the origins of turbulence are multiple, but in fact the ones that we normally worry about are threefold. One are heat sources within the dome. These are ones that you actually have some control over. We've got no real control of the atmosphere, but we do have control of what happens within our dome, and that's why we cool our mirrors, we refrigerate our domes, we make sure that the wind flow through the dome is as laminar as possible. That's why all of those Boeing CFD studies that Rebecca showed you are so important to the design of the telescope, because any seeing that you lose within the dome is entirely on you. It's not something you can get back, and it's something you will regret forever afterwards. So you spend a huge amount of time actually fixing the problem within the dome. But the problem within the atmosphere you can't fix, and typically there's at least two layers. Conceptually, there's a ground layer due to turbulence, due to the boundary layer where the wind is blowing over the ground and interacting with hills and all the rest of the structures, including your dome, and producing turbulence at very low levels, anything from a few tens of meters up to a kilometre. And then there is the high altitude winds, which is causing shearing in the upper atmosphere near the tropopause and stratosphere, and that's happening up at 10 or more kilometres into the atmosphere. And so there are different layers that we can think about which are producing the turbulence which is causing our blurring. Now, if we had a perfect telescope image, then the point spread function, which is just the intensity profile of a point source, without turbulence, would look like a nice Bessel function, and it would be the full width half maximum would be the diffraction limit, so roughly lambda on d, where d is the diameter of your telescope and lambda is the wavelength that you happen to be working at. So for example, lambda on d is 0.02 arc seconds for 1 micron and a telescope of 10 meter diameter. So the Keck telescope, for example, when it's working at 1 micron, should in principle be able to form images of 0.02 arc seconds. But with turbulence, the image size is typically much larger. In fact, perhaps as much as 2 orders of magnitude larger, between 0.5 and 2 arc seconds. And this is the natural seeing. Okay, so when we're trying to characterize turbulence, the critical parameter is Fried's parameter. And Fried's parameter is essentially the coherence length, the distance over which the optical phase distortion has mean square value less than or equal to about 1 rad squared. And at a good observing site, that number will typically be 15 to 30 centimetres. So in other words, the coherent patches of atmosphere are typically 15 to 30 centimetres across. Now, just to remember as a quick conversion factor, a 10 centimetre Fried parameter corresponds to a full width half maximum of 1 arc second at around about half a micron. So there's a nice number to get in your head that you can scale from. And the critical point to remember, of course, is that the larger the coherence length, the better the seeing. So larger R0, better seeing. Larger coherent patch, ideally a coherent patch as large as your primary mirror. But of course, given our primary mirror is 25 meters across and the patch might be 25 centimeters across, that's not going to happen without some work. So if a telescope diameter is much bigger than the coherence length, then the image size for point source is lambda on R0 rather than lambda on D. And that means the seeing disk is much, much larger than the diffraction limit. So R0 can be thought of as the diameter of the circular pupil for which the diffraction limited image and the natural seeing limited image have the same angular resolution. So if we say that R0 is 25 centimeters at a good site, and that's a very good site, any telescope larger than this diameter has no better spatial resolution. So once you've got a 25 centimeter telescope, you're seeing your point source doesn't get any sharper as you go to bigger diameters. For GMT, the diffraction limit is potentially 100 times sharper than the natural seeing. So how do we realize that advantage? Well, the answer is through adaptive optics. We're trying to take the blur out of the atmosphere in essentially the same way that your noise-cancelling headphones take out the background noise to the music that you're listening to. So the first step is to measure the turbulence. You can't deal with things that you can't measure. So you measure the details of the blurring by looking at a guide star. You actually take a reference source, you stare at it, and you figure out what the distortions are doing. You know it's a point source, you know you're not getting a point source, so you can infer the turbulence, or in fact the distortions that are occurring. You can actually then compute the shape of a deformable mirror that you need to apply to invert that effect, and so take out the blurring. So the light from the guide star and the actual star that you want to look at is reflected from the deformable mirror, and if you've done it right, if you've correctly measured and calculated what the distortion should be, you should be able to take out the distortions, provided, of course, that you can close this loop faster than the distortions actually change, which typically means you need to be running at kilohertz rates. So here's the sort of effect that you can get from adaptive optics. Without adaptive optics, you've got this speckle image here. With adaptive optics, you've vastly sharpened up the intensity of your point source. So in fact, what you've got with adaptive optics is some mixture of a diffraction-limited image core with scale lambda on D and a seeing-limited image halo with scale lambda on R naught. And the Strahl ratio, which is used to typically characterize adaptive optics, is the ratio of the peak intensity of a point source to that produced by a perfect optical system. So if you've got a purely diffraction-limited system, you've got a Strahl of 100%, and for anything less than that, you've got some lower Strahl. Now, when an AO system is working well, both the system and the atmosphere are obliging, then you'll have more energy in the core, more like a diffraction-limited image, and less in the halo, less like a seeing image. When an AO system is stressed, for example, by poor seeing or because you're kicking the optics, the halo contains a larger fraction of the energy. And the ratio between that diffraction-limited core and the halo varies both with conditions and the performance of the AO system you've got. And that's characterized typically by the Strahl ratio, although we also use the encircled energy within the peak from time to time. So here are AO images of a binary star, just some examples. On the right, blurry images of the binary star, and then with adaptive optics. These are some very old adaptive optics dating back from the late 1990s, provided by Claire Max. And here's a schematic for how an adaptive optics system would work. Yes, that would be better. I keep tripping over this one. So here's, is that working? Okay. So here's a schematic of the adaptive optics system. So AO has to operate in some sort of loop. It can be open loop, as I'll show you, but typically it's operating in a feedback loop, a closed loop. The next cycle is correcting the small errors of the last cycle. So the light is coming in from the sky, from the telescope. You've got a distorted wavefront. It hits an adaptive mirror, which is correcting that wavefront. And so the corrected wavefront should be more like a plane parallel thing. That wavefront is going through a beam splitter. Some of it's going through to your science instrument, in this case a high-resolution camera, but some of it is going to a wavefront sensor, which is actually detecting the residual distortions from the plane wave. And those residual distortions are measured by the sensor. They're run through the control system, which corrects the deformation, and then you apply a new correction to your deformable mirror, which is then sending a new correction down the loop. And so you're cycling through this closed loop all the time, rapidly enough that you are hopefully seeing many samples of your wavefront, distorted wavefront, before it is changed by the atmosphere. So the deformable mirror, of course, is simply a piecewise approximation to the real wavefront. Real deformable mirrors have smooth surfaces, but they're pushed by locators on their back. And in practice, each deformable mirror is simply a small bendable face sheet with actuators sitting behind it. This is usually placed after the main telescope mirror. So Here's some example AO applications. Again, these are from the early days of adaptive optics, and I'm sure Rebecca will show you much more modern ones. Here, for example, finding a faint companion around a bright star. This is two images from Palomar of a brown dwarf companion to GL105. Here's a coronagraphic image. You can see the faint companion there is a bit blurry. Here you can see it as a very sharp dot using an adaptive optics system. Another one, you can see two infrared images of Neptune at 1.65 microns in the near infrared, without adaptive optics on the left, just a big blur, and on the right you can clearly see the band structure in the atmosphere of Neptune. Here's another image, Uranus with the Hubble Space Telescope on the left. Hubble, of course, doesn't have to worry about atmospheric blur. This is an image in the visible. On the right is a Keck AO near infrared image, and you can see that in fact the Keck image is superior to that of Hubble, because Hubble is a 2.5 metre telescope, even though it's in space, and Keck is a 10 metre telescope. All right, so that's how AO works, at least schematically, but there are some problems with single star adaptive optics. If you've got a single guide star, then in fact you can only correct a narrow field of view because of what's called the cone effect. And the cone effect is that your telescope is only seeing light from the single star through the cone of the atmosphere running between the edges of your... Go back to the other one. Oh, right. So you can only see the distortions of the atmosphere in the cone that is actually being sampled by the light rays from the star. So in order to fix that, the answer is clearly, as in most astronomical things, more stars. And so you've got missing data here that you can fill in if you add more stars to the system. And so here in a multi-star system, you can actually sample multiple cones and fill out the atmosphere over the whole area covered by your mirror. And so with multiple guide stars, this tomographic AO approach allows you to reconstruct the turbulence in the entire cylinder of atmosphere sitting above your primary mirror. Okay, now there's a range of different AO configurations, and this is the menagerie of acronyms that we talked about before. First of these is single conjugated AO. This is the simplest possible system. You've got one natural guide star and one deformable mirror here. Here's your telescope. You've got a high altitude layer of turbulence and a second ground layer. This is obviously very schematic. You've got your telescope, realised here is this block, and then you've got your ground conjugated dark mirror and an on-axis wavefront sensor. And so this deformable mirror here is essentially conjugated in this optical system to the ground layer deformation. So it's only picking that up and only able to correct for that through the wavefront sensor. And it can only do that over a relatively narrow field of view for the reasons we just talked about. With laser tomography AO, which was the second system I talked about, you can have a natural guide star. In fact, you generally need a natural guide star plus a few laser guide stars so that you've got a small man-made artificial constellation of stars, and that covers your field and allows you to sample the entire structure, and that means that you are doing a better job of sampling that single conjugated layer, usually the ground layer, but it could be any layer that you pick. But one can get fancier. One can have multi-conjugated AO. One can have the same natural guide star plus a constellation of laser guide stars, but two, or indeed more, deformable mirrors, which allow you to be conjugated to multiple layers in the atmosphere. And then you can look at that with the wavefront sensors and correct that. And there's multiple ways of doing that. You can either have the multiple wavefront sensors feeding through it into a nonlinear correction in the wavefront correction system, dealing with both of the deformable mirrors, or you can conjugate each layer separately and have the two deformable mirrors directly conjugated either to the ground layer or the high layer through a single wavefront correction system each. You can also get even fancier, and instead of trying to correct a wider field of view with multi-conjugate AO, you can actually use multi-object AO. So whereas the whole point of multi-conjugate AO is that you get correction over a wider field of view, albeit with some penalty in your peak strail, with MOAO you don't try and correct the whole field, you only try and correct the pieces of the field that you're actually interested in. So you simply correct a narrow field of view around each object of interest, but at many places over a wide field of regard. And you do this in open loop. So you can see in this particular case, because this is not covering this whole field of view, you're just correcting locally here, you're simply projecting ahead in open loop and predicting what the deformation of the mirror should be in order to correct the last distortion that you saw. And you can do that in many, many locations if you wish. And then finally there is ground layer AO, where you are again looking with at a constellation of guide stars, but only trying to correct the ground layer, but doing it very thoroughly by sampling the entire field of view. And this provides a relatively modest correction, but over a very wide field of view. So these are the various flavors of adaptive optics, and all of them are of interest to GMT. So here's the sort of predicted effect that might hope to be obtained with ground layer adaptive optics on GMT as a function of wavelength. And as with all adaptive optics, things are easier as you go into the infrared. And in the infrared, you can in fact take an uncorrected median full width half maximum of 0.35 arc seconds or so, 0.4 arc seconds or so, and bring it down to about 0.1 arc second for a single target. However, if you want to do that over a 5 arc minute diameter field, that costs you quite a bit in the full width half maximum in the Strahl level, and you can only bring it down by about a factor of 2, out at around 2 microns. As you move back towards visible, you still get gains, but they become proportionately less. Around about 1 micron, you're getting a gain of around 20 or 25% rather than the factor of 2 that you're getting out at 2 microns. Okay, so that's a quick introduction to adaptive optics, how it works and why it's good. Let's do a similar thing with multi-object spectroscopy and integral field spectroscopy. So multi-object spectroscopy is exactly what it sounds like. It's the ability to get spectra from many objects simultaneously, but importantly to do that over as wide a field of view as possible. Imaging multi-object spectroscopy actually images the whole focal plane and uses slits to isolate targets of interest. On the other hand, fiber multi-object spectroscopy is a bit like the MOAO. It only collects the light where you actually care about the targets. It collects light at or around each target of interest using either a single optical fiber or a group of optical fibers. And this allows you to be much more flexible and to use your detector space much more efficiently and to look at much wider fields of view. Integral field spectroscopy is simply spatially resolved spectroscopy or imaging spectroscopy. It's obtaining a spectrum at each pixel of a small image area. And of course one can combine the two. Multi-IFS is multi-object integral field spectroscopy, and it does exactly what you might imagine. It gets an integral field spectrum, a resolved spectrum, a spatially resolved spectrum of each object over a wide field of view for many objects simultaneously. So if we can get past the acronyms, we can actually think about what this actually does. So it's an important question, whereas it's obvious just how important adaptive optics is for these very large telescopes. One immediately sees the gains. It's not quite so obvious that multi-object spectroscopy, wide field spectroscopy, or integral field spectroscopy will necessarily be important for ELTs. ESO actually did a poll of its community back in 2015, asking what are the 3 most important capabilities for your research after 2020, so both in the VLT and the ELT era. And interestingly, 40% of responses put some form of MOS or integral field spectroscopy facility as one of the top 3 priorities. And in the optical and near infrared, that was in fact 80% of responses. So in fact, it turns out that an enormous amount of science actually wants to use either multi-object or integral field spectroscopy on these big telescopes. Multi-object spectroscopy is really most potent for science programs that need to observe either or both of large numbers of targets, so high multiplex, high numbers of things observed simultaneously, or large areas of sky. And the natural metric for this is in fact the survey metric A omega, which is a product of your telescope aperture in meters squared and the field of view in square degrees or radians or whatever. But of course, other factors like the multiplex advantage or the seeing or point spread function, because of that gain in reducing the sky background, can also be, of course, very important depending on your particular application. But it's worth just looking at A omega because that's something that's specific to a telescope, whereas multiplex and other things depend on the instrument or the adaptive optics. So ELTs can access very large numbers of objects because they're so sensitive. Even in a small field of view, there can be very large numbers of targets. But the giant apertures mean that the fields of view are relatively modest, and hence, in fact, they have relatively modest A omegas. For example, GMT plus MANIFEST has got the largest A omega product of the 3 ELTs. The expected gain from GMT compared to TMT or ELT with their widest field visible spectrographs is in fact a factor of about 6 over TMT and a factor of about 4 over ELT, despite the very much larger apertures, because of MANIFEST's ability to capture that entire 20 arc minute field of view. On the other hand, these A omega numbers are not very impressive compared to, say, for example, the biggest survey instruments like PFS planned for Subaru, which in fact is a factor of 2 better than GMT plus MANIFEST. And even my modest little UK Schmidt telescope and Taipan system, even though it's got a dinky little 1.2 metre aperture, its 6-degree field of view means that in fact it wins big on A omega. So clearly A omega is not everything, and these other factors, the seeing, the reduction in the background, the ability to see faint sources, and a high multiplex and a dense field of view, play a very big role in determining which of these various systems is going to be most applicable to your science. Now, whereas MOS is a complex question and depends very much on the science that you want to do, integral field spectroscopy is a very natural combination with ELTs. And the reason for that is that integral field spectroscopy almost invariably suffers from photon starvation. Particularly in galaxies, the surface brightness profiles decline rapidly, typically exponentially, with radius. And so very soon you're finding that you've run out of photons if you want to actually image that bit of the galaxy far out from the center. Also, if you want to look far back in cosmic time, cosmological surface brightness dimming is a real killer because it goes like 1 plus z to the 4. Combine those two things together, as one usually does, it's incredibly challenging to do spatially resolved spectroscopy of galaxies either far out in radius or far back in redshift, and in particular both at once. So here's where the sensitivity of ELTs can really make a big difference. So ELTs offer significant gains in 2 ways. As big light buckets, they immediately offer a d-squared advantage in the amount of light that they can capture. And with the adaptive optics, if you're using adaptive optics as well, then they can offer a further d-squared gain via smaller point spread functions, reducing the amount of background that you're mixing in with your target of interest. Now, you might ask, how do ELT's smaller point spread functions help when you're looking at galaxies, which of course are extended sources? And the answer is, of course, to the extent that the surface brightness profiles are smooth, they don't help. But in fact, the surface brightness distributions is generally structured and at least partially unresolved, even by ELTs. And in fact, as you go further back in redshift, galaxies become more and more structured, more and more less smooth, and so, in fact, you do get greater gains. So, for integral field spectroscopy, ELTs can offer gains somewhere between d squared and d to the fourth. And as a result, it's no surprise that, in fact, all three of the ELTs have first-generation integral field spectrograph instruments. On the European ELT, there's Harmony. On TMT, there's IRIS. And on GMT, in fact, there are going to be two. GMTIFS is an integral field spectrograph. That's what the IFS in it stands for. But MANIFEST is also capable of providing integral field spectroscopy when coupled to GMAX. So let's have a quick look at these three instruments. TMT plus IRIS. IRIS is a near-infrared 0.85 to 2.5 micron instrument. It's a medium-resolution spectrograph, R of about 4,000, and an imager covering about a 17 arc-second square field. It's got a range of different spatial scales from 4 milliarc seconds up to 50 milliarc seconds, and the field size scales appropriately. This is the system here. It's complex, and I'm not planning to go into it here, but it has separate imagers and spectrograph arms for the system. Harmony is a similar sort of system, but with a wider spectral range. It actually goes down to around half a micron and up to 2.5 micron, and offers a wider range of resolving powers from 500 to 20,000. It's got 32,000 spaxels in the near-infrared and 8,000 in the visible, and those are arranged in a roughly √2 to 1 aspect ratio field. And again, the spaxel scales are range from about 0.06 to 0.03 arc seconds down to 0.004 arc seconds, running from what they call ultra-sensitive, coarse, meaning you gather more light, down to diffraction limited, the very fine sampling. And it aims to have a high throughput, of course, as they all do, and operate in a variety of different AO modes. Just to give a comparison, in seeing limited conditions, it should be able to offer a gain of a factor of 25 in speed relative to μ's on the VLT. On the other hand, it can provide similar angular resolution to ALMA and comparable sensitivity to JWST. So where does that leave GMTIFS? So GMTIFS is a AO-corrected integral field spectrograph, and that's building on our experience at the Australian National University in building the NIFS integral field spectrograph for Gemini and the WIFES system for our own 2.3 metre telescope. And it's also a high-scale AO imager, which builds on our experience building the GSAOI system for Gemini. It works in the near-infrared. We're not pushing down into the optical. It works from 1 to 2.5 microns, and it works with both laser tomography AO and natural guide star AO. So if we're using it as an integral field spectrograph, you can have spectral resolutions of 5 or 10,000 and a range of spatial sampling and fields of view given there. And again, it's fairly similar to the other two, ranging from 6 milliarc seconds up to 50 milliarc seconds with correspondingly smaller and larger fields of view. But you can see the fields of view are all in arc seconds, a small number of arc seconds at most. So it's a narrow field instrument. It's also a narrow field AO-corrected imaging camera, in this case sampling at 5 milliarc seconds per pixel over a 20 arc second field of view. The science drivers for all of these instruments are very similar. If you look at the GMTIFS science case, then the three areas that really stand out are stellar populations and chemical evolution, the assembly of galaxies and first light and reionization, and the study of black holes. And in fact, if you look at the ELT and Harmony science case, or indeed the TMT case as well, you in fact see exactly the same fields coming up time and time again. So it's clear where we're actually aiming. We're aiming to look at stellar evolution and the galaxy evolution and black holes in the cores of galaxies. In the same way that there is an integral field spectrograph on each of the ELTs, there's also a multi-object spectrograph as well. GMT and TMT have both got first-generation MOS instruments, but the ELT has deferred that to a possible second-generation MOS. Again, on GMT, we've got two different options. There's GMAX itself, which is an imaging MOS system, and then you can couple MANIFEST to GMAX, or you can couple it to GCLEF. And so there's three different ways of doing multi-object spectroscopy. One imaging MOS with GMAX, and two fiber MOS systems for low resolution with GMAX or high resolution with GCLEF. On TMT, there's YFOS, as instantiated by the MOBI spectrograph. And then there's a concept called Mosaic for the ELT. So here's the TMT and YFOS instrument. The YFOS is the sort of generic name for this wide field optical spectrograph, and it's realized as the MOBI instrument. MOBI provides near UV to optical imaging, and then spectroscopy at low to medium resolution for a slit of about 0.75 arc seconds. And it does that over a 25 arc minute squared field of view, so it's just a 5 by 5 effective field of view. It will include an atmospheric dispersion corrector and will operate in natural seeing, so it can use uncorrected images. It has red and blue arms and then imaging in 3 different spectroscopic modes. It's a big and a complex instrument. Mosaic is a potential second-generation instrument. It's got 3 operating modes. One's called high multiplex mode, which covers the visible and near-infrared. One is high definition mode, which provides spatially resolved observations in the near-infrared. And one's a multi-light bucket integral field mode. So Mosaic is really both a MOS and an integral field spectrograph, but intended to cover a relatively wide field of view. The visible arm covers 0.4 to 0.8 micron, multiplex of around 200, resolutions of 5 to 15,000, and a 32 square arc minute field of view, either seeing limited or GLAO. In the infrared, 0.8 to 1.8 microns, similar resolution, slightly lower resolution, similar field of view. The high definition mode operates in the near infrared at RF 5000, and they're planning on having 10 IFUs each 2 arc seconds on a side with 0.75 milliarc second sampling. And that requires multi-object adaptive optics, right? That can't be done any other way on the ELT. Manifest, on the other hand, is a different system. Whereas MOBI and Mosaic are specific realizations of spectrographs, Manifest is actually a fiber facility system. It's very versatile, and it services all of GMT's natural seeing or GLAO-fed spectrographs. So that means GMAX and GCLEF in the first generation, and potentially NearMOS or other things down the track. So it's not really an instrument per se. There is no detector on Manifest. It will not actually catch any photons. It will just funnel them to another instrument. It's a facility for spectrographs. Manifest maximizes the use of the focal plane in the same way that AO maximizes the image quality. So Manifest is more like AO. It's an intermediate between the telescope and the instrument than it is an instrument in its own right. But because it's not tied to a particular instrument, it's very, very versatile. So it increases the field of view for all instruments. It means that any instrument that can be fed by Manifest can see the entire 20 arc minute field of view of GMT. It means that you can feed multiple deployable IFUs in a variety of sizes, limited only by your imagination and the area of the detector that you've got in your instrument. It can increase the spectral resolution of your instrument by doing image slicing on the sky, typically a factor of 3 to 8. It gives you very efficient packing of images on your detector. Because it's fibre fed, you don't have to let the images fall where they may. You can pack them in to make sure you use every pixel of your detector. You can feed a narrow spectrograph field from fibres with a wide optical field of view. You can do simultaneous observations with multiple instruments, and you can feed spectrographs at gravity invariant locations, such as GCLEF. And down the track, if we can get the technology to work, you can change out the fibres that we'll have on day one and insert OH skyline suppression in the near-infrared and actually massively reduce the near-infrared background that's flowing to your detector in a way that's extremely efficient and leaves very little residual. So it's a very versatile instrument and very powerful. And I'll talk much more about that in the third of these lectures. Okay, so let's now talk about the GMT instrument suite. Rebecca's already shown you a version of this diagram, and it shows you where the light paths go to get to the various instrument focal stations. And in fact, we care about all three of these focal stations for the instruments that I'm talking about. GMTIFS sits on the instrument platform at one of the folded ports. So it's sitting here, coming off the tertiary mirror here, and sitting to the side above the main Gregorian instrument rotator below. Manifest in the early days, before there's a wide field corrector, will sit here at the direct Gregorian narrow focus with no corrector, and that'll give it a narrow field of view up to 10 arc minutes in diameter or so. And once we've got a full corrector, which is shown in red, then in fact it can access the wide field, full 20 arc minute field of view. So in order to do that, of course, we've got to fit within the volumes that are available. There's no particular problem with GMTIFS. There's a volume assigned to it in the focal plane position sitting above the instrument rotator there, so it's fine. But we do need to fit manifest into one of the alcoves that sit below where we still need to leave room for GMAX, for potentially NEARMOS and other things in future. Fortunately, as I'll show you, GMAX is a relatively compact system and can easily be fit in there. It needs to slide out into the focal plane in order to access the field of view and needs to be coupled with the wide field corrector. So here again are our first generation instruments, and I'll just remind you that in fact Manifest is in fact feeding both GCLEF and GMAX in the instrument. So in fact in these talks I'm going to end up mentioning all four of these instruments. The only one that I won't be talking about at all is GMT NEARS. Okay, so let's think about the science that we have with these instruments. Both GMTIFS and Manifest, by their nature, are very versatile instruments. GMTIFS can do both high spatial resolution imaging and high spatial resolution spectroscopy. And it, in fact, addresses almost all of the different broad science cases in one way or another. The only one it doesn't really touch on is the cosmological physics. Likewise, Manifest, because it's got a wide field, because it can do multiplex, high multiplex, and because it's got integral field spectroscopy as well as multi-object spectroscopy, is again very versatile. It's feeding to very versatile spectrographs, and again, in fact, touches 5 of these 6 areas. The only one that doesn't really have much to say about is extrasolar planets. So these are both very broad fields of view. And so in talking about the science cases, I'll simply pick out a few highlights and give an idea of what these two instruments can do in some of these areas. So let's look at GMTIFS first. Before we can talk about the science, we need to think about what the requirements are. Now, in fact, the way this works is that you think about the science for a generic instrument which can do integral field spectroscopy and high-resolution imaging, and you write down some science. And then you see what the instrument can actually do, and you develop a spec. And then you rewrite your science case, and you fiddle with your spec again, and you iterate until you achieve some sort of convergence. And this is where we've basically ended up for GMTIFS. You can see here the very broad science applications that are listed, not quite as broad as the ones listed before, but these are 5 of the top science applications we expect to have from our extrapolated science case. And these are the sort of top-level requirements that they have. The wavelength range you'd like to access. Everyone wants all of the wavelength range that there is. And the spectral resolution required. Everyone wants at least 5,000 resolution. And the reasons why you want that in each case are listed here. And you can see that there's some differences there in the sort of adaptive optics spatial resolution that you want as opposed to spectral resolution. Some prefer a coarse pitch because they want limiting sensitivity. Some want the fine pitch because they want limiting spatial resolution. And those translate down into these technical parameters here: the wavelength range, the spectral resolution, the spatial resolution at fine pitch and at coarse pitch, the field of view at fine pitch and coarse pitch, and the image quality, where of course we want diffraction limited if we can get it. And we've set a throughput goal of at least 20%, and we hope to significantly beat that. So these are the very top level goals, and then you break that down into lower and lower system level requirements in order to figure out exactly how your instrument needs to be built. But for GMTIFS, spatial resolution is key. Here is the effective size in arc seconds of various physical sizes of relevance: 100 parsecs, 500 parsecs, 1 kiloparsec, as a function of redshift. And of course you see the well-known effect that once you get above a redshift of 1, the angular size corresponding to a fixed physical size changes very little. So over a very wide range of redshifts above 1, 100 parsecs corresponds to a bit larger than 0.01 arc seconds. 500 parsecs is around about, what's that, 2, 3, 4, 5? Yes, 0.05 arc seconds. And 1 kiloparsec is a bit larger than 0.1 arc second. And you can see that these are different ranges that we can be sampling with GMTIFS, and it's worth comparing that to what JWST can do up here. So it's all about the spectral resolution and about having good enough AO that you're getting close to the diffraction limit wherever possible, or wherever you need to, in fact. And the reason that makes a difference is because the difference between natural seeing and what GMT can really produce is truly enormous. This is natural seeing at the typical seeing found at Las Campanas of around about 0.6 arc seconds. This is what HST can do on the NICMOS instrument. This is what JWST can do with a 6.5 meter mirror rather than a 2.5 meter mirror. And here's what we expect to be able to do with GMT if we can achieve a strail of 80%. And if we blow that up, you can see that this same field is unrecognizably different. Not only are we seeing much finer detail in the field, but we're also seeing many, many faint sources that are simply not apparent in even the HST image. So this is meant to be a little movie, but it's not playing. Can we get the movie to play? Well, it's a movie probably you've seen before, but each of those dots is a planet orbiting this star. Don't worry too much, it's not critical. And each of those dots, you can actually see them orbiting the star in this lovely AO image. So that's the sort of thing you can do with good AO for planetary systems. And in fact, here's a simulation that was already shown at least once, showing here's the best that can be done at present. This is a VLT L-band observation, suppressing the light of the star and detecting this 10 Jupiter mass planet here. Here's how well we would detect that simulation if we were working out at L-band. And then this is what we'd see: 2 Jupiter mass, 1 Jupiter mass, and even half a Jupiter mass very close into the star, sort of at the limit of detection. Quite extraordinary what's possible. GMT will be able to image giant planets out to 150 parsecs and Earth-like planets within 10 parsecs. Oops, that was interesting. Okay, another movie that's not doing anything. So on the left is the well-known movie from the Keck UCLA group, showing the stars orbiting around the black hole, the centre of our Milky Way. And on the right, that's the actual sort of image that one's dealing with. What they're doing here, of course, is centroiding all those blurry blobs in order to get those positions. But with GMT, this is the sort of resolution we can get, and so we can do a far superior job of studying the properties of the stars orbiting our own Milky Way black hole, and so get far better constraints on the parameters of the black hole, but also study what happens to stars when they pass very close to the event horizon. Again, if we want to look at galaxies out at high redshift, for example, a galaxy out close to the peak of star formation at a redshift 2, then one can compare this model galaxy on the left with what you would see in an HST image and what you can do in an H-band GMT image, again achieving a Strehl ratio of around about 80%. And you can see the enormous difference in the amount of morphological information that's available there. You can actually see the structure, the spiral arms, the bar, and so on in this galaxy. So GMT gains in angular resolution can be summarized in comparison to what's currently achievable on an 8-meter telescope by this plot. This shows angular resolution in milliarc seconds, so the 1000 at the top is 1 arc second, as a function of wavelength, basically in the optical and near infrared. The top of this range is the 8-meter diffraction limit, and the bottom is the GMT diffraction limit, defined by the 1 on lambda on D Rayleigh criteria. The dashed lines show GMT's 3 and 5 lambda on D resolution for contrast limited case, so where you're trying to look at a planet around a much, much brighter star. And you can also see the seeing limited and GLAO resolutions that do not scale with aperture. So those are pretty nearly fixed for an equivalent AO system. And you can see there's a very substantial gain on this log diagram in the scales at which one can actually look at these things. And over on the right, you can see at a distance of 100 parsecs that we're resolving not 100 AU, but say 20 AU. And out at redshift 1, we're resolving not of order 10 kiloparsecs, but of order a couple of kiloparsecs. So these are very substantial gains that we are making. Likewise, GMT gains in sensitivity, the other big gain that we're making with going to a bigger telescope, can be measured in this plot. This shows the 5 sigma limits in 1 hour sensitivity in millijanskis or in AB magnitudes on the right. And again, the top of the range is the 8-meter sensitivity, and the bottom of the range is GMT sensitivity in blue for natural seeing in the optical and near infrared, and in the near infrared and out into the mid infrared for adaptive optics systems. And you can see the enormous gains that one's getting, both for imaging, which are the bars in various pass bands, and for spectroscopy, which are the 2 curves. And of course, the seeing limit applies down, is the only thing you'll get in the visible, but in the near infrared, with adaptive optics, one gets a very large gain indeed. So what are we going to do with these gains that we're going to realize with GMTIFS, both in sensitivity and in resolution. Well, one of the things we can do is look at the very highest redshift galaxies that we can look at. First light galaxies, for ELTs with adaptive optics and integral field spectrographs, should be able to really characterize and look at the properties of the very first galaxies to light up in our universe. And potentially, depending on what you think the properties of POP3 stars are, maybe even individual population 3 stars, or at least clumps of population 3 stars. So here's a simulation on the right. This is actually from the TMT and IRIS group, looking at the population 3 stars forming in these orange regions, which show the very dense, pure hydrogen helium gas in this still forming galaxy. The overlay is a 1/3 arc-second field of view, roughly the IRIS field of view, and you can see the sampling is getting close to this 0.025 slicer scale that IRIS will offer. So you should be able to actually see each of those clumps of POP3 stars if they have the properties that are expected. Not quite at such a high redshift, but going out to redshifts between 1 and 5, we should be able to use the same sorts of systems to trace galaxy formation and mass assembly over that redshift range, using the well-known emission lines to map the 2D dynamics of galaxies during that peak epoch of star formation and AGN accretion. And I'll talk some more about that here. So here are a set of channel maps, so slices in velocity space along the line of sight, for a simulated GMT plus GMTIFS observation of a galaxy. So we took a Hubble Ultra Deep Field I-band image of a real galaxy, a clumpy looking galaxy. We pushed it out to a redshift of 1.5. We then imposed a completely arbitrary 200 kilometer per second rotation field, just to have a rotation field on our galaxy, and then simulated what we would get with GMTIFS. And I'll talk about how we do that simulation tomorrow. The simulation here involves 50 milliarc-second spaxels, so relatively coarse spaxels, and we've assumed a total line flux of around 1 × 10⁻16 ergs per centimetre squared per second. We've then observed it for 12 hours, 9 hours on source and 3 hours on sky. And you can see then that we're mapping out this velocity field in extraordinary detail. We're keeping all of the structure in this galaxy and seeing all of the rotation field as well. This is an extraordinary amount of information for a galaxy out at a redshift of 1.5. All right, let's have a quick look then at what we'll be doing with MANIFEST. So again, MANIFEST, here we've got the technical requirements. We're talking about 3 different modes. Basically, mode A is GMAX mode, visible single fibers or IFU bundles, low resolution spectroscopy. Mode B is near infrared mode. This is for NIRMOS, single fibers, low resolution spectroscopy. And mode C is GCLEF, visible single fibers, high resolution spectroscopy. And you can see that there's a wide range of things, starting with star formation, massive galaxy assembly, chemical tagging and Milky Way structures, dark matter distributions, evolution of clustering and tomography of the IGN, and these operating mostly in the visible here, because that's where we're concentrating for the first light instruments. Mode A and mode C are our first light instruments, and then different resolutions, some of them low, medium, and very high, depending on what we want to do. And this is the power of MANIFEST, that it can be so very flexible by interacting with more than one instrument. So here are the requirements. It's got to cover at least the visible range with the first sets of fibers. In fact, we'll have multiple sets of fibers, some optimized for the visible, some optimized for the near infrared. The patrol field of those fibers will be the full 20 arc-minute diameter available. Positioning accuracy will be better than 0.1 arc-seconds RMS. And in fact, there we've got an enormous advantage in the huge plate scale of the GMT, where 1 arc-second corresponds to 1 millimetre. So 0.1 arc-second is not, in fact, very challenging. It's, in fact, 10 times harder to do, in fact, 20 times harder to do on the UK Schmidt, where we're doing our prototype system. But we can keep our setup time small, hopefully just a few minutes. We'll keep our throughput through the fibre system very high, and we'll maintain quite high multiplex factors in these different modes. In fact, depending on how you want to set this up, you could potentially have of order 1,000 single fibres if that's what you wanted to do. Of course, these all couples to the GMAX requirements, which I'm not going to really go through, but I'm putting them there for reference. But of course, since Manifest is feeding GMAX, most of these flow through from the Manifest science case, and likewise the GCLEF instrument requirements. Okay, so one of the things that we'd like to do with Manifest, one of the areas where it really shines is by increasing the multiplex that GCLEF can offer by perhaps as much as a factor of 40 or so. Instead of looking at a single star at a time, we can, over specific narrow wavelength ranges, do high-resolution spectroscopy for up to perhaps of order 40 stars at a time. And that means we can collect detailed chemical abundance information and other sorts of high-resolution spectral information for large numbers of individual stars, both in our own galaxy and in nearby satellite galaxies. And that means we can then study the process of galaxy formation, not only in the Milky Way, but in a range of other galaxies as well, and study different galaxy formation histories in quite detail. Because we'll have initial mass functions for stars and star clusters, we can track the chemical evolution, and we can quantify the effects of various processes responsible for radial migration. And we can do that in a range of different galaxy types. So with GMAX and GCLEF, GMT is going to be the only ELT that is capable of doing this science. Neither of the other ELTs will be able to do this sort of science. With Manifest, GMT can actually offer wide field multi-object spectroscopy with both GMAX and GCLEF. And that means our opportunities include understanding the origins of galactic extremely metal-poor stars and doing full membership identification and self-enrichment histories for some of the newly discovered low-mass galactic satellites. And these galactic archaeology results then have major ramifications for fields ranging from nuclear astrophysics, stellar astrophysics, all the way through to galaxy formation. So, for example, if we wanted to look at dwarf galaxies and stellar streams, we can take the large-scale imaging projects that currently exist, like DES and PAN-STARRS, and of course, in future, LSST, which are finding many more new low-mass galactic satellite galaxies. Now, these low-mass galaxies represent galaxy formation in a very different regime to the Milky Way. Low masses, low density environments. By coupling GMAX and Manifest, we can obtain low resolution spectra for hundreds of stars simultaneously over a 20 arc-minute field of view. This means we can get relatively high quality, signal-to-noise ratio of 80 or so spectra, for stars brighter than the main sequence turn-off in ultra-faint dwarfs out to 100 kiloparsecs in 2-hour exposures, and in just 10 minutes for dwarfs as close as 40 kiloparsecs. And in fact, half of the discovered dwarfs so far are closer than 40 kiloparsecs. That means we can do quick assessment of the membership of and kinematics of these low-mass dwarf galaxies. We can do fundamental stellar parameters, and we can do a subset of elemental abundances and maybe even ages for these key objects. Another way of looking at this is near-field cosmology, the study of the formation history of all the components of the local group to understand how it was assembled and the conditions and processes that operated in the early universe. By combining GMAX and Manifest, we can efficiently characterize the metallicities and velocities for large numbers of stars in local group streams and use chemical fingerprinting to link those individual stars to their birth cluster. Stars that are torn apart in a tidal stream can be tied to a single origin by looking at their unique chemical fingerprints. And that means we can then reconstruct what these tidally distorted or even destroyed structures looked like originally. They can then be compared to the surviving systems to understand how mergers and tidal debris contributed to the assembly of the Milky Way and other local group galaxies. The faintest known galaxies in the local group are all gas-poor with uniformly old stellar populations, and that just reflects the conditions in which they formed. And so by studying them, we can understand how the earliest galaxies formed. The low metallicity stars in these ultra-faint dwarfs tell us about the very first supernovae to go off, what type of supernovae they were, and how did they enrich these tiny galaxies, and how did that enrichment end when the galaxies were still very small. So for a nearby system like Segway 1, GMT could obtain chemical abundances for every known member star and get a full picture of the star formation and chemical enrichment history of this incredibly low metallicity and therefore presumably very archaic galaxy. And that gives us a window into those very early epochs of star formation. LSST in future is going to discover hundreds of these ultra-faint galaxies well out beyond the virial radius, and it'll provide us with star formation histories through JWST based on resolved colour magnitude diagrams. If we build on that LSST and JWST data, the spectroscopic observations that GMT can give us will give us detailed dynamical and chemical maps of these nearby galaxies out beyond the edge of the Milky Way's dark matter halo. And by studying these fossilized remains, perhaps tens or maybe even hundreds of local group galaxies, we should be able to, again, get another window on the first phase of galaxy formation that's simply unobtainable by any other method. Now, as well as looking at the fossilized remains of early galaxies, we can actually push back and look at galaxies in the process of forming at high redshift. An 8-hour integration with GMATS and MANIFEST gives us a signal-to-noise of 5 of the rest frame UV continuum for a 0.1 L-star galaxy at a redshift of 2, i.e. at the peak epoch of star formation, or for a 0.5 L-star galaxy out as far as a redshift of 5.5, just after the epoch of reionization. In a few tens of nights, GMT could potentially survey as many as 10,000 low-mass galaxies over that redshift range from 2 to 5, map out the properties of the interstellar medium and the stellar components of these young galaxies over this long baseline, which is the first few billion years of star formation up to the peak period around redshift 2. But you can go further than that. In doing that sort of survey of the properties of galaxies, you can also map the cosmic web. We have to remember that the universe has got 12 times as much matter in diffuse gas as in stars, and that by looking at the cosmic web both through emission from gas excited by nearby stars and by the absorption of light from background objects passing through that gas, we can actually look at the complementary views of matter in the different physical states as it falls into galaxies, is excited within galaxies, and then ejected from galaxies in this gas transport cycle through the circumgalactic medium in and out of galaxies. So here we've got 3D views of the cosmic web and emission, where we're stepping through velocity channels of emission line gas, or in absorption, where we're using background objects to look at the total emission, total absorption along the line of sight to that background object. Now that gas flowing in and out of star-forming regions can be imaged in the line emission using an integral field spectrograph, and the 3D density and velocity fields can then be reconstructed by tracing the line-emitting gas in both the spatial and spectral directions. The relative strengths of the common lines give us the underlying gas density, the relative motion and other properties, and then you can take that 3D data cube and invert it in order to get the mass flow rates in and out of galaxies, plus the spatial variations in the chemical enrichment and the ionizing radiation. And all of that's possible by using that wide field optical IFU on MANIFEST and GMAX at medium resolution. And in doing that, we actually have a system which has a 5 times greater survey speed than Keck or the VLT for such studies. So here are the sort of things we can do. We can actually map the hydrogen gas around galaxies. we can look at the distribution of the heavy ions, we can measure the gas covering fraction, and we can map the galaxy outflows by looking at the absorption line spectra of many background sources. And of course, we have many more background sources because with the big light collecting area of GMT, many more objects are suitably bright for us than is the case for an 8 or a 10 meter telescope. Finally, let's look at population-free stars and metal-free galaxies. If we're surveying galaxies out at redshift 6 to 10 with a near-MOS-like near-infrared MOS, then we can actually do the first systematic search for galaxies which have got metal-free stars. While galaxy formation is well underway at redshift 6, the metal enrichment from star formation is local and gradual, so that even at redshift 6 there are going to be patches of the universe which don't have significant metal contamination. And POP3 stars should still form in these underdense regions down at redshift 6, 1 gigayear after the Big Bang. Now, if the POP3 IMF favours very high mass stars, then the strong UV radiation will power nebula H helium emission, and the lack of metals will result in weak emission from the carbon and oxygen. And that means that we can actually characterise the strength of this helium-2 and metal lines in galaxies at redshift 6 using something like near-MOS. Since the POP3 phase is going to be very short, at most 10 megayears or so, these metal-free galaxies are going to be rare. So we're going to need to look at thousands of galaxies at higher than redshift 6 over a 1 square degree field in order to find even one of these objects. And that means we need to have a very large multiplex advantage, and that's something, again, that near-MOS is going to be very good at doing. So since these faint objects have got high surface densities, we should get a big multiplex advantage. With near-MOS and MANIFEST, we can target galaxies over a big field of view, 7 megaparsecs diameter at this redshift. And that means we can follow up lots of redshift 6 galaxies that, say, are identified by W first. And that's going to be impossible with JWST because it's got a much smaller field of view. In fact, we expect something like 300 redshift 6 or higher galaxies over that 20 arc-minute field of view down to the W first depth. So that number will go up by a factor of 10 if we actually look at the limit that we expect to get from some of the guaranteed time observation programs with W first. So the bottom line here is that thanks to its wide field capabilities, we only need 10 different pointings to cover a full square degree. No other planned or existing facility can hope to cover that sort of area. So again, we've got a really unique niche for MANIFEST and near-MOS on GMT. All right, so I'm going to wrap up there. Just to remind you, we've got this incredibly broad science case. I'll talk a bit more about it when I speak about each instrument in detail in the next 2 talks. And the thing I haven't talked about so far, and we'll mention again, although some of it's crept in, is just how all of these things integrate with all of these other wonderful facilities that we're going to have at the same time. In particular, new facilities that don't yet exist, like JWST, SKA, and W first. And I'll leave it there and take questions. Thank you very much.
So questions, please.
Not sure if this is a question or a comment or a mixture of the two. So you have been presenting the expected results from the high spatial resolution of the different instruments that will be installed in GMT. But I can't help feeling that we are mistreating other instruments. Now, for example, you are comparing the expectation, mistreating other instruments. No, for example, you are comparing the spatial resolution of the NICMOS and NICMOS camera in HST. Like NICMOS camera is a 10 years old camera. Now we have wide field camera 3, which has a higher resolution, better pixel scale, PSF, sorry, and then James Webb is coming now, and you are not comparing with the new facilities. Now it's a new instrumentation with all instrumentation. I think this is unfair somehow. And my question...
well, let me just quickly comment on that. So first of all, I am extracting some of this from old science cases, and so these were the relevant instruments at the time, and clearly in the new GMT science book, we will be comparing to the latest instruments, because that's the relevant thing to do. nonetheless, even compared to the newest instruments, there are gains. They're just not quite as large as some of the pictures I've shown you here.
So the question was, how does it compare now, the high spatial resolution expected from this instrument, how does it compare with James Webb, for example?
Well, they're both nearly
state-of-the-art
diffraction
linear
limited, right? So it's a factor of 3 in aperture, so it's a factor of 3 in linear resolution, the first order.
Right, that's a good point.
More questions? You should really sit near.
What is the fraction of the natural sun that comes from the ground layer and from the upper atmosphere, more or less?
That depends on the site, and it depends on the day. So if at a good location, it's fairly consistent, and the amount of turbulence is between 30 and 50% in the ground layer. But a very interesting point is that the ground, how much turbulence there is in the ground layer is a very local effect that's caused in part by the topology very near the dome. So what you want is a very smooth slope up to the telescope so that a lot of that ground layer doesn't get lifted up into the dome. So I should be careful. It's not so much that the fraction of turbulence in the ground layer is local, it's that how much of it affects the telescope is a very local effect.
Becca's working very hard to make sure that ground layer adaptive optics does as little as possible.
Which would be good.
Well, let me, just as a question, take advantage that Rebecca has a microphone and you as well. So, all of that will depend on we having adaptive secondary mirrors. So right now, all the deformable mirrors are smaller than my hand. Am I right, or they are bigger than that? So so my question is, how much of technological breakthrough we need to make 1 meter diameter secondary adaptive?
Okay, can I go with this one? All right. So this is a beautiful point, because the adaptive secondaries for GMT are actually 4th or 5th generation, depending how you count, of the adaptive secondaries that are made by a company, or now a combined company in Italy called Ad Optica. So the adaptive secondaries, the first one was on the MMT, the second one was probably on LBT or Magellan. I'm not sure the order there. So they're in total on MMT, LBT, Magellan, and the VLT. The VLT, I think, has the most recent one. So they are nearly identical in size to the individual adaptive secondaries on GMT. So that's one of the interesting things about this double segmentation. So the improvement in technology is a very small step in the actual deformable mirror. And in every generation, as you can imagine, the electronics are getting much more reliable, and the implementation of the fabrication for the secondaries is getting much better. They're doing, whatever went wrong in the last generation, in the last one, they're applying to improve the reliability of the next one. What's interesting about GMT is not the mirror technology, or even particularly the electronics. It's the closed loop control of all of those 7 mirrors together. So I think that's really the jump in technology and in interest on these on GMT.
It's software, not hardware.
That was the short answer.
More questions?
Getting out of AO, going to manifest, just to balance a bit. You mentioned, and Rebecca mentioned this morning, that manifest takes 5 minutes to reconfigure. Now, what I was thinking of, I was thinking about the fiber positioner of Giraffe on VLT and the fiber positioner on Weave, and they have 2 plates, and each plate takes, can't remember, an hour to reconfigure, right? So is that also going to be the case that there's going to be two plates being reconfigured at the same time?
I'll show you how it works, but in fact, you can actually reconfigure these in 5 minutes on a single plate. So the starbucks, the little individual fiber position, move around on the plate. And in fact, 5 minutes is basically a worst case scenario. If you don't need to move them very far, it can be significantly less. The other really neat thing about it is that you can actually, move it during the observation, if you like. So in fact, over that wide field of view, atmospheric differential motion means that in fact the relative positions of things change over the field of view. But the starbucks can actually move in real time during the observation to track that and actually keep your star centered in the fiber over that period. You have to do that open loop, but it's not that hard to do it. We believe that's perfectly possible. Rebecca's looking nervous. I'm not looking at her, but I'm sure we can do it.
More questions? You can ask questions for everybody now because we can consider we are in the discussion session as well.
I just would like to understand a little bit better the manifest. So you can like make an IFU with the fibers. Is that what you're saying?
Yes.
And which is the size
I
of
will
the
be
sky?
talking more about this in my third lecture.
Oh, okay.
So I'll show you that. But the answer is yes.
Mm-hmm.
We already have made some example star bugs with quite sizable IFUs on them. So the question is, how big could we make them and before they become too cumbersome? But clearly, IFUs as large as the ones we already have on SAMI, which have 69 fibers in them, that we're sure we can do.
Okay. Thank you.
So I didn't understand how manifesting can increase the spectral resolution for GMAX. Could you explain this?
Just by image slicing. So all it does is it puts a little IFU, say a 7-element IFU on your star, right? Splits up the image, so it reduces the size of the image, and then you put that on a slit, and so it's like putting a little image slicer down across your star, splitting it up so that the star is split from this wide to this wide, and so reducing the spectral resolution as well. Increasing the spectral resolution, reducing the spectral width.
Is that okay? So let's thank Matt and all our speakers again. And we reconvene tomorrow, 9 o'clock, okay? Thank you. Thank you very much.